Head on Fire is a Patreon-supported podcast. Supporters of the show get early access to ad-free episodes, a private Discord server, archives, and more. All benefits are offered on a sliding scale, so no matter your level of donation, you never miss out. If you like this show, consider supporting it with $1 a month or whatever you can at patreon.com/headonfirepod. Thanks, and enjoy the show. If you live on planet Earth, you're probably aware that the trailer for the new Ant-Man movie just came out. It's a movie called Quantumania, and a big part of Ant-Man's storyline, or at least as it pertains to his involvement in the Marvel Cinematic Universe, involves something called the quantum realm. In fact, throughout the MCU's cinematic history, the words quantum and quantum physics and quantum mechanics and quantum realm are used quite a bit. They're a pretty good stand-in for any time any of the movies want to say the words science magic, but can't, and they want to make it sound a little bit more official. Why can you time travel? Quantum physics. Why can you teleport? Why can you, shrink down to the size of an atom? Oh, it's all quantum physics, quantum mechanics, quantum. But this is not a new thing, and it's not relegated to the Marvel Cinematic Universe. Anytime that just about anybody in any field wants to make a strange, unfounded claim, you tend to hear the word quantum quite a bit. Let me take you back in time. The year is 2004, and a little, I'm gonna say documentary, because that's what they tried to pass it off as, and I'm not quite sure what else to call it, a film. A film titled What the Bleep Do We Know came onto the scene, and it was a precursor to the international best-selling phenomenon The Secret, and it was all about the law of attraction, and basically how our thoughts, our mind influences the world around us, and a whole lot of people in a whole lot of spiritual woo-woo communities pointed to this and said, look, science has finally proven what we've known forever. Quantum physics proves that our brains affect the world around us, and that what we think is what we summon into our lives. Look. We've proven it. Look at this flashy documentary. It was not a documentary. Pretty much every single claim made in the movie has since been disproven. But thanks to What the Bleep Do We Know and The Secret and millions of other books and movies and YouTube shows and all sorts of other crap that floats around on social media, the words quantum physics, quantum mechanics, quantum, and the law of attraction, spiritual stuff, pretty much any time that somebody somewhere wants to make a claim of outlandish powers, outlandish spiritual ability, the words quantum get used quite a bit. And so with the movie Quantumania coming out in the MCU, and sort of a resurgence lately in things like, in conversations surrounding like manifestation and affirmations and things, which is just kind of a new spin on the law of attraction, I wanted to finally pull the curtain apart and take a peek behind and see what is quantum physics. It's really easy to attribute whatever you want to a buzzword when nobody really understands what the buzzword means. When nobody can agree to a definition, it's really easy to make the word mean whatever you want it to mean, so much so that the word has almost lost its meaning. I invited onto my show Dr. Jed Buchwald. Jed Buchwald studied physics and science history at Princeton University and earned a PhD from Harvard in 1974. He taught at the University of Toronto for 2 decades, where he spent a year as the director of that university's Institute for the History and Philosophy of Science and Technology. He then became the director of the Dibner Institute for the History of Science and Technology and the Bern Dibner Professor of the History of Science at the Massachusetts Institute of Technology before joining Caltech in 2001. He has authored or co-authored 6 books on the history of science and, more recently, on the decipherment of Egyptian hieroglyphics. He edits or co-edits 3 book series for Springer, 1 for MIT, and 2 journals. He's a member of the American Philosophical Society, a member of the International Academy of the History of Science, and a fellow of the American Association for the Advancement of Science. He was also a MacArthur Fellow in 1995 and a Killam Fellow from 1990 to 1991. And he is my guest today. Here's Dr. Buchwald. Jed Buchwald, thank you so much for being here at Head on Fire. I appreciate you coming.
Pleasure to be here.
So for folks who don't know you, and you're not on TV, Oprah hasn't interviewed you recently or anything, so maybe folks might not know your public profile as much. Tell folks a little bit about yourself and what it is that you do.
Well, I am a professor of history here at Caltech. I've been here for over 20 years now. I'm a historian of science by training originally, a long time ago, and most of my work is in research and history of various aspects of scientific work like Newton and others. Although in more recent years, I've also written about Egyptology, the decipherment of hieroglyphs, and so on. It's actually all related, but different topics. And that's basically what I do. Then I run various book series, journals, and so on. The usual thing that professors do.
Sounds like you'd be the guy I'd want to corner at a party and just ask a million questions. So I'm glad I have you here at my party. So I have you here today. You are a science historian. I have you here today to talk about some science and the way that it has developed into our modern world, specifically quantum physics. That term has been in pop culture discussion since I can remember. The first time I really heard it was in a documentary called What the Bleep Do We Know, which talked about the supposed law of attraction, or The Secret, in which it seemed that the idea of an observer on reality affecting reality was sort of stretched to mean thoughts or things. Anyways, in the years since, the term has been used in film and television to mean a kind of science magic. Basically, whenever the protagonist wants to do a crazy thing, the science character finds an explanation for why the thing is possible due to quantum physics. We need to look no further than the fast and loose way quantum physics plays a role in things like the Marvel Cinematic Universe. So my question, and I feel like a lot of people's question when they hear the term, is what is quantum physics actually?
Well, that's close to asking me what is the deep nature of reality in the universe.
That's question 3. No.
I am, although I'm trained as a physicist, I am a historian of physics. How shall I put this? Like almost any reasonably well-evolved area in the history of any aspect of science, it's a technical structure which is designed and evolved to explain certain fundamental aspects that are testable and observable of the way the world is, things that we can approach. And there's a long history to how quantum mechanics developed and whatnot. And it does sound very spooky to people when they first learned about it, because the world is seen through the window, if you will, of quantum mechanics is not a world that really consists of things that we normally deal with on a daily basis. It does involve particles, but it also involves aspects of particles that are not what one would normally think about. You can't shoot a quantum mechanical object directly at a target with a certain speed and be sure that it's going to hit just where you aimed it. That's not the way the world works. It's much more complex than that. And so the developers of quantum mechanics in the early parts of the 20th century eventually decided, and it took quite a while to come to a structure of this kind, that underpinning the world and every object in the world is what came to be called a wave function. I don't think of waves like we normally do. although this is a mathematical object, which has certain properties that are similar mathematically to what waves are. Mm-hmm. But it isn't a wave like a water wave. In fact, unlike waves that we normally deal with mathematically, it's made up out of complex numbers, partially imaginary numbers, things that are very different, but that mathematically have a well-articulatable structure. And what this thing does is that when you, as it were, multiply it by itself, actually what's called the complex conjugate of itself. Anyway, you do something with it. And what it determines is the probability that an object, like an electron, will be found in a certain region or will have a certain speed. It can't have exactly a certain speed and be somewhere. In fact, if it had a very precise speed, it could be almost anywhere. On the other hand, if you know very precisely where it is, you really have no idea whatsoever what its speed may be, actually its momentum, and so on. Anyway, the point is that although this sounds spooky and strange, from our point of view, it leads to highly testable experimental consequences, which we live with today. You're looking at me, and I'm looking at you through an object which is grounded on the laws of quantum mechanics. The very microchips and microstructures that govern the internet are in fact the results of quantum mechanical interactions at this very low microscopical level and so on. Now, although mathematically you can handle things when you structure an experiment very well, and you can even do experiments on things that are very strange, but that work quite well. Nevertheless, there is an ongoing issue with, if you will, the conceptual underpinnings of quantum mechanics. And let me try and make it as, and I am no expert on this, but let me try and make it as simple as I can. When I said a few moments ago that if you try to shoot an electron through an opening, you can't shoot it and get it to hit a target you aim at precisely. There's only probabilities of where it'll be. Now, when I said that, I implicitly was separating out the object with the opening in it from the electron itself. And what I'm doing when I do that is I'm not treating the object it's going through as though it too were governed by the laws of quantum mechanics. I'm making an impossible object, actually. And this leads to what's called the measurement problem of quantum mechanics, that it is in order to work through experimental situations and so on, you have to send your objects to interact with things that you don't treat quantum mechanically. And so there is this kind of deep problem, which most physicists, at least until fairly recently, have not been interested in. I can tell you a little story. When I was taking physics, I was an undergrad and a grad for a while at Princeton, way back in the 60s. We took a course in quantum mechanics from a famous professor. There were only about 13 of us in the class at the time. In fact, he'd written the book. His name was Robert Dickey. And I still remember he's at the blackboard and his back is to the class. And on the blackboard, he writes the equation. It's called the Schrodinger's equation, which governs quantum mechanics. Okay, so he writes it down and everybody's hand went up. Because everybody wants to know, well, okay, I've heard about that, but what does it really mean? And I still remember, without turning around, he said, gentlemen, it was all men at Princeton in those days.
Sure.
He said, gentlemen, put your hands down. It's given by experiment. We will now calculate the hydrogen atom. In other words, stay away from those icky questions that I just mentioned a moment ago. And so I can't really answer the question you told me, or you just asked me, except to give you a sense. We can calculate. We can even do some very spooky things, such as with quantum information theory and so on. But it's all consistent mathematically until you start asking about this deeper question of how these objects treated quantum mechanically interact with measuring apparatus, which you don't treat quantum mechanically.
I want to ask a really dumb question, and it's so I just want to define a couple of terms here that come up when discussing quantum physics, quantum mechanics in different articles that I've read. What is a particle? Because I have some questions on my list here that I have made particle a synonym for the word thing. Oh, it's just a thing. Is it like a proton, neutron, electron, quark, somewhere in that realm? Also, what is an observer? What counts as an observer?
Well, okay. The particle thing is usually it's used for any object whose behavior requires the use of quantum mechanics for determining what's going to be going on, even using probabilities. So these are micro objects, the size. And the size, even an atom on the whole, would be rather large for most of these things. Electrons, neutrons, at the lower levels, quarks and things of that kind, which make up other particles. And these are all governed by the laws of quantum mechanics, in particular by what's called the standard theory, which has been developed in the last 60 years or so. And that works. That works. It works very well for calculating stuff. Now, you ask, what is an observer? An observer is, loosely speaking, the measuring device that I just mentioned a few moments ago. It's any kind of, loosely speaking, it tends to refer to a macroscopic object, an object that you don't treat quantum mechanically, which is interacting with an object that you do treat quantum mechanically.
So I think that what a lot of people hear when they hear observer is they center the human experience, right? They think of, well, when we're looking at it, when we as humans are looking at something, it's that when the tree falls in the forest, in question. But it's not that. It's not us, right?
No, it's certainly, well, I mean, we can be observers in that sense, but we are merely macroscopic, that is, large-scale, non-quantumly treatable objects.
So when I hear the word observer, I hear the word observer in tandem with a particle or something exists when we're looking at it and it doesn't when we're not, or something like that. I'm very dumb. I majored in criminal justice. So, but when I hear the word observer, it almost sounds as though, or at least in the articles that I've read by on who knows how reputable the websites are, that the observer is in some way informing what they're looking at. That they are creating what they're looking at or causing what they're looking at. Is any of that true? And if not, how did we get there in thought?
Well, the last thing you says, the observer is causing what they're looking at. Let me take off the looking at business, because an observer is a measuring device.
Yes. Okay. Sorry.
It's not it could be, it could be this pen if it's interacting with a particle and so on. And when a measuring device treated non-quantum mechanically, as I said, interacts with a particle, or a quantum mechanically treatable object, then, how shall I put this? The quantum mechanical object is reduced to one of what are called the possible states that it can exist in. And by states, you can have states of position, states of momentum, states of energy, states of time. That is it here at a certain time? Is it in et cetera, et cetera? And this quantum function called the wave function determines the probability given the surrounding structures that the object will be found in one of its states when it interacts with those surrounding structures. So you can't say that it's in any, that, you know, it's not like the particle is flying along and there it is, and we just don't know where it is. No, that's not how it's generally thought about. The particle is itself intrinsically bound to this wave function, and until it interacts with a non-quantum object to produce a measurement, like you're shooting electrons through a little slit, there's a screen, and when an electron hits the screen, the spot that it hit glows, okay? Well, you don't know except what the probability is where it's going to hit. And you can't say it's specifically anywhere until it is reduced to one of its possible existing states, which you can predict only probabilistically.
Is that the double slit experiment? Is that I have that on my list to ask you about, because that also seems like science magic.
Sure, actually, I was referring to a single slit, but the same principle holds actually, although the mathematics is a little different, just as it is in light. Yes, because this wave function is governed mathematically by equations that are similar to the ones that hold for, say, light, and in the usual classical sense, if you it's like passing a wave through two slits. If you imagine a water wave, okay, there's a big water wave. The wave goes like this, and here's two. It's in the ocean, and we have two barriers, and there's two holes, and the wave goes through there. Well, when the wave hits each part, it sends out little waves from those parts, and those waves, they interfere with one another. And so they've produced big crests and low troughs and so on. Well, the same thing, mathematically at any rate, happens with the wave function. But the troughs and the crests are the probability points which determine where you are likely to find the particle when that spot shows up on the screen.
I want to ask, turn from trying to define what quantum physics is, as I think we've very well established it's kind of difficult to define. There have been a lot of conversations in the last year or so, a lot more articles being published about this next subject, time. The idea that time isn't real, that our perception of time is just an illusion that our brain is making up to get us through life. I was asking some of my listeners if they had any one question for you, what would it be? And several of them put through, do you believe in time?
All right. Let me first say, I hate a question which is aiming at a kind of scientific thing, which uses the word believe. Belief has nothing to do with it, nothing whatsoever. I don't believe in the theory of evolution. I find it a well-grounded scientific structure backed by considerable evidence. Belief has nothing to do with it. Okay. You want to talk about religion, we can talk about belief.
Sure.
Okay. That's a different issue. Time is, within the context of both quantum mechanics and relativity theory, one of the parameters that determines how the structure works. Now, since the early 20th century, with the development first of special relativity and then more complexly of general relativity, the conventional notion of time, in which people would think that, well, if something happens here at a certain time, then somebody 3 billion miles away still has the same time for when that thing happened. Let's say an explosion happened. Mm-hmm. Okay. Well, no, they don't, because time functions as one of what are called the coordinates mathematically in a 4-dimensional, not 3-dimensional space, the space of space-time. And in that, it's perfectly real. There's nothing unreal about it at all. And it works very well mathematically. It does mean that we had to alter our technical understanding of what it means to say that 2 events occur at the same time. What does it mean to say they are simultaneous? Those are different meanings depending on how you want to do it. And so in physics, physicists speak of the space-time coordinates of an event. And in the mathematics of space-time, if you take 2 events, one occurs at a certain time, at a certain position, and another occurs at another time, at another position, okay, then we speak of the space-time distance in this 4-dimensional realm between these 2 events. And that space-time distance, is the same for different, well, uniformly moving, anyway, different observers, okay? But the measurable distance, as though if I were to take, for instance, my ruler here, somebody would measure a different physical distance at a different place in space-time, and would, if they had a clock to measure the time between 2 things, they'd have a different time. But the spatial distance put together with the time difference using a simple formula is the same for all observers. So we replace our normal understanding of physical separation with this separation in what's called space-time. And there's nothing imaginary about time at all. It's just that it has properties that one would not intuitively find obvious.
I think when I say time is imaginary or something like that, I think what I'm referencing is this idea in sort of pop culture right now that our future selves, our past selves, our present selves are all coexisting at the same time. We just can't see them because we perceive time as linear thing. And according to quantum physics in the articles and the pop culture and stuff, it isn't linear, and all of those things are happening simultaneously. We just can't see it. But if we had the right perspective, we could. Does that have any relation to what you understand the science to be?
No. All right. Oh, there you're pushing things to the ultimate speculative end as to how we understand these things and what the ultimate nature of the universe is, whether there are multiverses, multi-universes, and so on. No. In the universe we exist in, okay, with all the galaxies that are out there, and so on, all the way back to the moments after the universe came into being as we know it. Time functions. You can't go. It doesn't mean anything to go backwards in time, really. There are ways of thinking about it in sort of extreme physical theories, which are mostly non-testable and so on, involving multiple universes and so on, maybe. If you ever saw the movie Interstellar, for instance, and that was the science advisor was one of our friends here, Kip Thorne. Then the guy is floating around and he looks at himself from before and so on. Well, there is no physical theory worked out, grounded on experimental structures in full detail that would really fully lead you to something like that, though there are, speculative possibilities. But in the practicing world of physics that my friends operate in, that I know about, that's nobody's going back and doing something to themselves when they were babies.
So y'all don't have any DeLoreans at Caltech anywhere in a in a garage somewhere?
Not that I know about. Not that I know about.
Can I ask about quantum computing? And I know that you referenced technology earlier, quantum computing and what impact that will have on the technology available to just regular people like us in the years to come.
Well, I mean, this really pushes anything I know very far, although here at Caltech, John Preskill and others are some of the major investigators in quantum computing. So, to the extent I understand it, which is not very deeply because it's a technical endeavor, it depends on what's known as coherence. How shall I try and put this? Because it sounds very spooky. Let's say within a certain region, two particles are interacting with one another. And in quantum mechanical sense, they cohere. That is, certain properties that each has are linked together, although you don't know except probabilistically what those properties values may be. Now, one particle goes off over there and another particle comes here. And when I measure a certain property of particle A over here, because of coherence, particle B will necessarily have a certain property related, certain value of property related. Now that sounds spooky because does it mean this guy's sending a signal to that guy? No, it's not sending a signal to him. They're connected coherently. You can't use that to send messages faster than light. You could do this. You could say to your friend sitting next to you here, okay, we're creating these two particles. And you talk to, let's say he's sitting somewhere else, you talk to him over the phone, and you say, I'm creating these two particles, and in the future, in a day, I'll create these particles, and I'm going to measure the particle I keep, and then I will know what measurement you're going to get over there. And if you get measurement A, I want you to do something. But if you get measurement B, I want you to do something. And I will then know what he's going to do without having spoken to him since then. But I don't have to send him a message. I set it up ahead of time. But I don't know which of the two things he's going to do until I make the measurement. Quantum computing is connected to this question of coherence. Don't ask me much more than that.
So I want to ask a question that I feel like a lot of people who are like me, that are inquisitive people, that like knowledge for knowledge's sake, and want to learn things, and are sort of fascinated by, current science news and stuff, have alerts for it on my Twitter feed and all of that. I feel like I at least understand how I interact on a daily basis with the fields of biology or chemistry, and even just straight up regular physics. I feel like I have a good understanding of how they impact my daily life, how they are used by experts in different fields to impact my life. Um, but what about quantum physics? How does the average person interact with that science right now, and how might we in the future?
Well, I mean, as I said, anything that you use electronically nowadays is basically grounded on quantum mechanical structures. That's how they work at the chips, the structures on the chips down at the nanotechnology level. These things are based on quantum mechanical properties. Every object that you use that way these days, since microchips are in everything, including your cars, uh, uh, when you're talking to Siri, you're talking to something which is grounded on a machine, if you will, that is quantum mechanical in nature. So we're interacting with quantum mechanical objects in the modern world in every possible way, maybe even more so than people in the 19th century who interacted with trains traveled on trains, because not everybody traveled on a train every day, but everybody I know is looking at their cell phones all day long. And those are quantum mechanically based.
Did the Big Bang Theory, the TV show The Big Bang Theory, help or hurt the public's base knowledge of quantum physics? I feel like there's a whole lot of people whose touch point for quantum physics are things like Big Bang Theory, Marvel Cinematic Universe. The new Ant-Man movie is Quantumania. Doctor Strange even just talked about multiverses and quantum mechanics and stuff. Uh, how are these references helping or hurting the field of quantum physics as far as it relates to its interaction with the public at large?
Well, I don't think there's anything wrong with it at all. These movies, silly though a lot of them are, are nevertheless quite amusing. And the idea that, the world that physicists and engineering physicists deal with and work with and so on is connected to these things I don't see any particular problem with that. Quite the contrary. Why not? If it excites anybody, as long as some 15-year-old doesn't think that he or she is going to grow up and make a time machine or something like that. But that they might want to be an engineer or a physicist or a chemist, that's fantastic if it does that. I know that a lot of the Caltech students around here, they watch this stuff. They've played video games and so on. Even I play video games, and there you're living in a very interesting space, which can lead people to be more interested in making careers in science, technology, engineering, and medicine. And we can use more people doing that, not fewer.
No press is bad press, right?
Right.
What excites you about the field right now? What are you looking at? What's the next horizon that you're looking at? Who are the people you're watching? What are the next developments?
Well, that's hard to say. I'm not a physicist. I am a historian, which means I deal with things sometimes hundreds of years old, not what's happening right now. It seems to me, from what I see around, that a lot of the most interesting work is being done with the properties of complicated structures down at the very micro level, how to work and analyze such things. And the other area that is always extremely interesting is investigations in astrophysics and astronomy, probing the properties of the early universe and so on. That's a big topic at Caltech, has been for a long time. And it remains extraordinarily interesting with lots more to discover. I mean, we don't really know. We can't get past the minuscule moment in time after which what's called the cosmic microwave background, which we can measure, came into being. In other words, we don't really know what happened. There's all kinds of theories and so on. But a lot of structures are fairly well attested, including something called inflation, which is like a giant expansion of the metrical framework of space-time after things came into being. But what happened at creation, it's who knows so far. There may be traces, even some of this multiverse stuff. There are physicists I've read about who claim that if there are multiverses, they may have left traces in the cosmic microwave background, which might be measurable and detectable. There, it's beyond anything I could speak even remotely reasonably about.
I do like that your fields are science and Egyptology. I feel like those are the two realms where the most conspiracy theories abound, or something like a conspiracy theory. Do you have a favorite Egypt conspiracy theory?
Well, a conspiracy theory.
Oh, just all those strange rumors that end up on the History Channel at 1 a.m. where, I don't know, the pyramids are trying to tell us something from some kind of aliens or something.
Yeah. Yeah. Okay. No. No, they're not. The pyramids are telling us many interesting things about Egyptians, more than 4,000 years ago and so on. And there's still an awful lot to be learned about that. The reason I got into the subject at all was because of history of science. It was many years ago. My wife and I were in Paris at some meeting or other, and we went to a bookstore. In those days, there were still bookstores, those physical objects which have, pieces of paper in them.
I've written 3 of them. I know, yes.
Good. And I always ask my students that, at this point. But anyway, we went in and wandering around, I was looking for old 19th century mathematics and physics texts, but I saw something in the corner which had in gold stamped on the cover the French word zodiac, meaning zodiac. I opened it up and there were pamphlets from the early 1800s about this Egyptian zodiac ceiling, which had sort of a description of the zodiac on it. And that had been brought to Paris after Napoleon and so on, and it generated a controversy because some scientists, astronomers, were claiming that you could date it to 13,000 BC, and this was after the restoration of the French monarchy, which was deeply religious, but brought it into conflict with religious convictions on the age of the earth and so on. So with one of my former PhD students, who was a novelist, Diane Greco-Josefowicz, we wrote a book on that. And then we decided to pursue it further, because one of the characters was involved, to how the hieroglyphs were finally read. I don't like using the word decipherment too much, though it's meaningful, because when you say decipherment, people tend to think about something that's hiding something, and you're going to decode it. It has multiple meanings, but so we wrote a book on that. So that's how we got into that. So it originated in a kind of science topic, but then evolved. Although one of the 2 protagonists, Thomas Young, was one of the great scientists of the early 19th century, early 1800s. So I knew about him. I'd written some stuff about his science before. So that's how we got into it. And my wife and I traveled twice to Egypt, where I was able to photograph where that ceiling was cut out. And it exists now in the Louvre in Paris. And it is one of the 2 earliest examples of what I would call archaeological depredations, cut out and brought to Paris, leaving a giant hole in the temple where it had been, Temple of Dendera. Even Champollion, one of the decipherers of hieroglyphs, the early 1800s, hated that had happened as a sort of archaeological vandalism. And the Egyptians would dearly like to have it back today, but I don't think the French are going to give it back.
I think there's a few museums out there where I think a lot of people want to just empty them out.
Yeah.
Give everything back to where it came from. For folks who might be interested and aren't quite sure that they want to dive all the way in, how can folks get started learning more about physics, quantum physics, engineering? What's a good starting point for them?
Well, there are so many relatively well-written, popular books on various aspects of these things that I cannot hesitate to really recommend anything in particular. But if they were just to go on Google and start looking around, or Amazon Books, they'll find plenty of things which can sort of bring them into it without delving them too much into the depths of, complicated physics. Although that's interesting.
It is very interesting. I've learned a lot. I feel like I'm going to have to go back and listen to this interview 5 or 6 times to figure out what it is that I learned, but I feel like I learned a lot. Jed Buchwald, thank you so much for being here and sharing so much of your knowledge about a topic that isn't very well known to a lot of people. We don't, like you said, we interact with it on a daily basis, but we might not understand what it is that we're interacting with, at least the layman. For folks who might be interested in you, your research, your work, where could folks learn a little bit more about you?
I have a website. I think it's, what is it? I never use my own website, so it's hard to say.
That is the answer that everyone that I know who has ever had a website, including myself, has to say, wait, what's my website? Right. What's my own email address?
It's jzbuchwald.caltech.edu. And it has, it's not very elaborate. It has various things on it, including a list of stuff I've written.
Well, I'm sure folks are going to be really excited to go read that. Thank you so much for your time. I really appreciate you being here. You have a good rest of your day, sir.
Bye-bye.
And that is going to do it for this episode of Head on Fire. My thanks to my guest, Dr. Jed Buchwald. If you like this show and you want to support it, there are a number of ways to help. Consider sharing it with your friends on social media. Doing so, you can like or rate the show 5 stars on places like Apple Podcasts or Spotify and leave a review. Remember that telling your friends about a show you like is the best way to help it grow. Reviews help recommend the show to other listeners like you. So, a couple words, a couple of emojis, your favorite quantum physics joke or something like that. Any of those in the comment section on those review sites really help the show in the ratings. If you hate the ads at the beginning and end of the show, consider joining my Patreon on a monthly basis. Patrons receive additional audio and video content, as well as archived episodes, a private Discord server, and occasional special treats. Sign up at patreon.com/headonfirepod. You can also connect with me on social media. I am at Head on Fire Pod on places like Twitter, Instagram, and TikTok. I have a pretty good feeling like this will not be the last time that we talk about quantum physics on this show. In fact, I know it will not be. So if you have any questions about quantum physics, anything that Dr. Buchwald said in the interview that you might want to get some clarification on, find me on social media or email me at contact@headonfirepod.com. Make sure to put something like quantum or quantum physics in the subject line so I know to tuck those questions away for the next time we talk. Thank you all so much for tuning in. Thanks so much for downloading and supporting the show. I'm going to go, but remember that quantum physics does not prove the law of attraction, and anybody that tells you otherwise is lying to you. Bye!